Howdy, everybody. We're going to look at simple harmonic motion. So we're going to tackle these kind of one at a time, but let's give it a go. Let's put my whole head in there. So first one, we got ourselves a person in a rocking chair. So this is starting with number 7. The ones before that, I don't want to just put answers here because I really want you to stop and think about those ones. But number 7, we got somebody in a rocking chair. Now, somebody in a rocking chair, they do 17 cycles in 16 seconds. So I'm going to start with going, okay, 17 cycles per 16 seconds. I'm going to get a value for that. I think it's like 1 about that. So 17 over 16, I get 1.06. 1.06 hertz cycles per second. Now that's not the period, that's the frequency. How do I find the period? Well, I would do 16 seconds over 17 cycles, and I get 0.94. So that is my time for one cycle. Well, if I go here, the old equation we started using is 1 over the frequency, and I'll get the exact same number. So T stands for period. All right, we're on number 8. Cool. So number 8. So quick review. So on these ones, you will drag them around. And if they're the same, you drag them into the same spot. If one's more, one's less, you drag it next to it. So just a review on number 8 is that the period is 2 pi square root of L over G. So what is it that really is going to impact these? Their period? It says rank them according to the number of cycles per minute. So if you have a big period, you will have a small frequency. But if you have a small period, you will have a large frequency. In other words, cycles per second. So what is the defining factor of these? I'm going to argue length. Number 9. All right, so number 9, we're going to get into a little bit of numbers. So I'm going to walk with you. It takes a force of 12 newtons to stretch a spring 0.16 meters. So start there. This is number 9. Force equals kx. So you apply 12 newtons, and it stretches 0.16 meters. So you can get a k value. Let's get what that number is, okay? 875. So I have my spring constant, okay? I have that. I can use that now. It asked me, and now I'm going to attach 3.2 kilogram mass to it. I'm going to let it bounce around. So period equals 2 pi square root of m over k. So the period is 6.28 square root of m over k. Plug in the calculator. We have different numbers, remember. You get 1.297 seconds for the period. So that's 1.3 seconds. Okay, that's my period. Frequency is 1 divided by period. There we go. Oh, and the units. The units for frequency will be h lowercase z, hz. All right. Simple pendulum consists of a bob of mass m attached to length L. If the bob's mass is double, what's going to happen to the new period? Well, period equals 2 pi square root of L over G. Is mass involved? No. So the period will be the same. If the period is brought on the moon, well, if you change this to a smaller g, it's g over 6. Well, if you plug in g over 6, well, that's square rooted. So that's like, let's see, we have L over G, but then over 6 is going to get me. So if I divide the G by 6, that puts a 6 up here. So I could factor that out. I could factor that out and get 2 pi square root of L over G. So this is what I started with, but by going to the moon, my period got bigger by the square root of 6. So my old period was just t, my new period is square root of 6t. All right, all right. Chains of swing, 3.4 meters long. We're looking at number 11. Hopefully I'm still recording. Yep. So period is 6.28 square root of L over G. Since we're dealing with mastering physics, we want to have this G be 9.8. AP exam, my test, 10's great. Okay, almost every class you'll touch will have just use 10. Mastering physics uses 9.8. I tried to make it so it accepts the answer, but if it doesn't, try using 9.8. Do it again. So we're going to plug in the length of 3.4 meters, and I get a period of 6.28 times square root of 3.4 over 9.8, get 3.7. There it is. So what is the period? There you go. 12. Lots of force faces in the way. All right, spring constant. What's the spring constant? Well, this is a good review. Number 12. If this is force and displacement, the spring constant is rise over run, which is force over displacement, which equals K. Since F equals Kx, if I divide both sides by x, I get F over x. So I get my K, my slope. My slope of this line is K. Slope of the line on the picture is 5 over 25 centimeters. So 5 newtons over 0.25 meters. So we get 5 divided by 0.25, I get 20 newtons per meter is my K. So there's part A. Part B, what's the period? So period equals 2 pi square root of m 0.10 kilograms over K. There it is. Plug it in, get a number. Part C, part B, no C. All right, here we go. 13. If you dribble a basketball at a frequency, this is number 13, at a frequency of 1.7 hertz, how long will it take you to do 17 dribbles? So that's actually kind of an interesting question. So it's 1.7 cycles per 1 second. Okay. How many dribbles do you want to do? 17. So what I would do is I would find out what the period is. It's 1 over frequency. So 1 over 1.7. I'm just going to get a number. We're going to talk about what that number means. I get a 0.588. 0.588 seconds per cycle. Now, what is the cycle in this problem? It's a dribble. So if you do 17 cycles, 17 dribbles, what do I do to this number? I multiply it by 17. So the total time will be times 17, 10. So it'll be 10 seconds. All right. It's kind of a weird problem, but I left it in there. I like you guys. All right, 14. Mass undergoes something. All right, 14. So the period is 6.28 square root of m over k. So we have a spring bouncing. It gives me the time, 0.61. It also gives me the mass. Now, it wants me to solve for k. Now, you got to take it easy on this one. You got to do a step at a time. So divide by 6.28 first. Okay, I get 0.097 equals the square root of 0.50 over k. Now, the next thing I have, I'm going to change my color for my next step. I need to square this thing. Okay, so I'm going to square that. I get even a smaller number. Okay, I get 0.0094 equals, now the square root's gone, so 0.50 over k. This is kind of where the math gets a little trickier. K's on the bottom, we get k on the top. So multiply both sides by k. So I get k times 0.0094 equals 0.50. What do I do next? I got to divide that. I'm going to change colors just so you can see my steps. Divide this out. So I get a k of 0.50 divided by 0.0094, I get 53. It's a little bit harder math, right? Because you're having to solve for not only something on the bottom, but you have other things you have to do before you can get there. All right, 15. 2 pendulum, 3 meters long. Period of pendulum A is T. Pendulum A is twice as heavy as B. Oh, no. Not telling you. 16. Pendulum oscillates with a frequency. Ooh, we got a pendulum and a frequency. All right, we're going to look at number 16 here. So number 16, we have a frequency of 0.60 hertz. I don't want frequency. I want period. So period is 1 over frequency, so 1 over 0.60. So I get 1 over 0.60. Get 1.6, a whole bunch of sixes. Okay, that's my time. That's my time. So period equals 2 pi square root of pendulum L over G. Period 1.667 equals 6.28 square root of L over 9.8. I want to use 9.8 because I'm doing mastering physics. First thing I want to do, I'm going to change colors for my first step. First step, divide by 6.28. Divide by 6.28. Okay, just do that first. I get this number. I'm not going to say it out loud because I wouldn't follow if I said that out loud. The next thing I need to deal with is this square root. Well, how do you undo a square root? You square it. So I square both sides. I'm just going to write down what I get, 0.0704, just writing it down, equals L over 9.8. What's happening to the L? It's being divided by 9.8. So what do? I multiply both sides by 9.8. So if I multiply both sides by 9.8, I get 0.69. Okay. Again, look what they started with. They gave you frequency. I need period because I have an equation for period. All right, let's get into period. Okay, now when I solve that math mistake that almost everybody makes is get rid of the number in front first, then deal with your next steps. All right, number 17. Which moment, we're going to actually go through this one. Which moment corresponds to the maximum potential energy? Where does that happen? A, looks pretty good. Okay. Which moment corresponds to the minimum kinetic energy? Where is it moving the slowest? A. When it's at the far end. Okay. Next up, consider the block in the process of oscillating. If the kinetic energy of the block is increasing, if it's speeding up, where is it? At equilibrium, no. Because at equilibrium, it's going to be losing right afterwards. Okay. Right before it's gaining, right after it's losing. Now, is it always going to be gaining? If it's going to the right, is it always going to be? No, it might be depending on which, are you past equilibrium or not? At the amplitude, how fast are you going? You're going 0, right before you lost energy, right after you gain energy. So I can't be that one, okay? If you're moving away from the equilibrium, you're slowing down. But if you're going towards equilibrium, you're speeding up because your maximum speed's at equilibrium. So as you head towards equilibrium, that's when you speed up. Which moment corresponds to the maximum kinetic energy of the system? When are you going the fastest? At equilibrium, point C. Point C, you're at 0 at the equilibrium. Now, which moment corresponds to minimum potential energy? When do you have the smallest potential energy? In this case, it's when you're moving the fastest. When you're moving fastest at equilibrium, that's point C. Now, point F, at which moment is K equal to U? This is the tricky one. I used to think, just a B. Oh, not really. It's actually going to be happening at point D. It's the spot where the kinetic equals the potential. The AP1 exam no longer makes this a have to. And so the moment where you have kinetic equals to potential, so at the ends, right, you have maximum potential energy. Well, that's going to convert into energy at some moment plus some kinetic at some moment. And so if you want to know when do these equal each other, well, at the end, well, if these are equal, that's the spot where you have at some unknown position, right? 2 at the unknown position. So kinetic energy at the ends is 1/2 k amplitude squared. Energy at some unknown, 1/2 k, we're just going to call it x. Okay. The halves cancel. 2 doesn't though. K's cancel. Okay, so I have a squared equals 2x squared. So I divide by 2, I get 1/2 of a squared equals x squared. When I solve for x, I square root. So the square root of 1/2 times a. Square root of 1/2 is going to be that point D where it's root 2/2. That is that's beyond AP Physics 1, but I just want to give you exposure to a way to solve that. 17G, I have it in the notes. If you've made it to 17G, please read the notes. Find the kinetic energy of the block at the moment labeled B. So at labeled B, I'm at A/2. So this is 17G. Again, this is going to be extra credit. This is not required. So now what's the kinetic energy? So the kinetic energy at that moment. So let's start with, what is my total energy? My total energy is that spring energy on the far outside. Okay. At point B, I have potential energy at B plus kinetic energy at B. Okay. So the total is 1/2 k a squared. The potential energy in the spring at B is 1/2 k a/2 squared plus 1/2 mv squared. So you're saying to yourself, what the heck? Oh, you know what we're going to do? It only wants me to find the kinetic energy. So I'm just going to label that K. All right. So I'm going to leave K here, but I'm going to subtract this over. It's kind of gross, right? I'm going to factor a 1/2 K out. So I have a squared minus a/2 quantity squared equals my kinetic energy. I'm going to put a KE here so I don't confuse it for spring constant. So I've got 1/2 K out here. Okay, a squared. I got to simplify a/2 quantity squared. So I get a squared over 4. Well, how am I going to put those together? I got to have common denominators. To have common denominators, I'm going to put this over a 4. So you get 1/2 of K times 3/4 a squared, which if I simplify it, I get 3/8 k a squared. That to me is awesome. It's just not AP Physics 1, but if you track that far, well done. All right, 18. Let's skip it. I don't need a grade. 18. So now it says rank the system according to period. So again, 18, period is defined by 2 pi square root of m over k. If you plug in the m and you plug in the k, you can find out which is biggest and which is smallest. If they're the same, put them on top of each other. So I'll show you what that looks like. If they're the same, let's say I'm like, C and D are the same. I put them on top of each other. If I think one's smaller, put it on the side. All right. On the moon. Think about what happens, changes on the moon. So you have period. Let's see, 19. Number 19. 2 little balls and you swing them and you go to the moon. Well, what's going to happen? Period is 2 pi square root of L over G. If you go to the moon, your G is less. So if your G is less, your period is more. So it'll take longer to complete one cycle. True. You'll execute more vibrations each minute. No, it's going to be all sluggish. Both systems will have the same period. No, they won't. On the moon, ball B will execute more vibrations. No, on the moon. Wait, who's ball B? Ball A is attached to a spring. Ah, geez. All right. 19. Screwed up. All right. 19. Let's start it over. Ready? 19. Here we go. Okay. So ball A, I read it wrong. Ball A is attached to a spring. Ball A. Ball B swings back and forth like a pendulum. System we're not taking the moon. All right. Is this guy going to change? No change, because period of a pendulum does not care about gravity. Now, the period of a pendulum does. If you change that, G is going to take longer. There you go. There it is. That's it. I'm not plugging in my answers. Next problem. Mass attached to a vertical spring. This is number 20. Big 2-0. Okay, sorry. Just had to get a moment. The mass exhibits simple harmonic motion between points A and B. Which of the following statements are true? The mass is located midway. Oh, jeez. Essentially, the mass is located. Wait, hold on. Mass is attached to a vertical spring. The mass exhibits several between points A and B. This is going to be the equilibrium in the middle that the mass is going to bounce back and forth from. Okay, it's going to go in between these. This is going to be equilibrium. The mass is located. It'll be here sometime. All right. When it's there, we have a huge kinetic energy. When I'm far away from it, I have all potential energy. Okay, so we're going to use that. Mass is located midway between points A and B when its potential energy is at a maximum. No! It is located between A and B when its kinetic energy is a maximum. True. It is going to be at A or B when its potential energy is at a minimum? No, when it's a maximum. The mass is located at A or B when its kinetic energy is a minimum. True. It's going really slow at the edges. All right, 21. 21. Motion diagram. Schmear, get my face out of there. Ready? What is the direction of the acceleration of the object at moment 5? When you travel in a circle, this is number 21. When you travel in a circle, what's the direction of your acceleration? The direction of the acceleration is towards the center, and that is direction A. So you just type in capital A, and that is it. All right. Part B. What is the direction of the acceleration of objects at moments 0 and 10? Uh-oh. It's going to get real. At point 0. Now, centripetal acceleration is v squared over r. But right here, you're not moving. So you don't have any centripetal acceleration. But where does it go a moment later? It gets pulled down the ramp. So the acceleration is in direction D, but when you get over here to the other side, the acceleration is going to be in direction F. Now, putting this in, I always have people, because you can't, I've learned, when I was in high school, I couldn't read either. Okay, so separated by commas, not spaces, not semicolons. So D, comma F. Put a space, you get it wrong. Okay, if you write it in words, you get it wrong. You gotta follow the directions. That is a hang up for people every year. But I like the question to think about what's the acceleration. How long does the pendulum have to be? I'm just going to set this one up. 22. Period is 2 pi square root of L over G. So if its period is 1.8, square root of L over, make sure you use 9.8. So divide by 6.28 first. Now you've got square root of L over 9.8. What do you got to do next? You got to square the whole thing. Okay, and then you have L over 9.8 equals some number. What do you do next? You multiply by 9.8. So we got 1.8, forgot the first number, divided by 6.28, square it, I get a number, 0.0821. Okay, what do I do to get L by itself? I multiply it by 9.8. I get a value, 0.805. There we go. Yeah, I know if you've been following the whole video, you're like, you've already done that one. But if you jump to 22, I got you. I believe these are starting to get to extra credit here. But if not, let's just keep going. Simple pendulum of length 2.5 meters makes 5 swings in 16 seconds. So sometimes they don't tell you what each swing is. 16 seconds for 5 cycles. Well, what do? 16 over 5. 3.2 seconds per cycle. What is the acceleration due to gravity at the pendulum? Well, I don't know. Period equals 2 pi square root of L over G. The period is 3.2 seconds. 6.28 square root of L. They gave me L. This is kind of weird. I'm solving for G. How do you think we figured out what G was? This is one of the methods. 0.50955 equals square root of 2.5 over G. Now I'm going to change my colors. I'm going to square now. Okay, when I square, I'm just going to square this guy. I'm going to write down what it is. 0.2596 equals 2.5 over G. Now what I got to do, I have to put it over 1 here. I need to now solve for G. So I move G up to the left, so I get G times 0.2596 equals 2.5. Now I divide. So 2.5 over that value, I get 9.6 meters per second squared. This is one of the methods we use to find out what G is. The more accurate your equipment are, the better you have an idea of what G is. All right, 24. Beginning the instant the object released, select the graph that best. Beginning the instant the object is released, select the graph that best represents the position versus time for the object. It's attached to a vertically oriented spring. The object is pulled a short distance below. Okay, so ready? So we gotta imagine this. Here's my equilibrium on number 24. And it starts here. Okay. If they pull it down, so I'm going to call this time 0, and then they let go. Okay. And then it goes up to equilibrium, past equilibrium, and then it comes back and oscillates. Okay. So set the origin of the coordinates to be the equilibrium position of the object. So this way is going to be positive, and we call this 0. Okay, so let's just start. Where does it start? Right here, it starts at a negative position. There's idea 1. Okay, it's going to start at a negative position. How fast is it going at the beginning? It's not going to be moving. Okay, so we're going to use those two things. So it starts at a negative position and goes to a positive. So graph that represents the position versus time. So if I look at my position versus time graphs, I'm going to put them over here so I can write on them. Okay. In these position versus time graphs, I'm going to think, okay, well, it says I start at a negative position. That's H and D. Those are the only ones that start at a negative value. But if it oscillates back and forth, I'm going to argue it's H. So that's a good position time graph. Okay. Next up, the next part B says, what about the velocity graph? Well, what type of velocity does it start with? It starts with 0 velocity. And then it gains a positive velocity. So it starts at 0. That one starts at 0. That one starts at 0. But right after time 0, it goes in the positive direction. That makes E good for a velocity time graph. Now acceleration. It starts with an acceleration pulling it upwards, right? That force is pulling it upwards. When it passes equilibrium, then it starts to experience an acceleration downwards. So it starts with a positive, which is F. And there's your acceleration time graph. All right, 25. 25. Pendulum. What's the length of the pendulum? So in this one, number 25, you're going to T equals 2 pi square root of L over G. So the period is 13 oscillations in 104 seconds. So it's 104 seconds for 13 cycles. Okay, so that's my period. 104 over 13 equals 6.28 square root of, do we know what L is? We don't. 9.81 will be my gravity. Off you go. All right, 26. Last one. Here we go. All right. I'm definitely making this one extra credit. Consider a block of mass M attached to a spring with force constant K. The block slides on a frictionless surface. When the spring is released, the block is located at x equals 0. Cool. After the block is released from x equals a, it will, when you bring it out to a, what's it going to do? Is it going to remain at rest? No, it's going to move to the left until it reaches negative a. And stop there. Is it going to stop? No, it's going to then come back. So it's going to stop and come back. All right, all right. Part B, the period is doubled. Ooh, frequency is halved. So remember how, let's see, the frequency is 1 over period. If I double my period, the frequency will have to halve. All right, see, oscillating takes 0.1 seconds to complete one cycle. What is the frequency? The frequency is 1 over the period. So it's 1 over 0.1. 1 over 0.1, shove it in a calculator, you get 10. See if he gets mad at me for not having the units, but it was off the screen. If the frequency is 40, what's the period? Ooh. Well, if frequency is 1 over period, it means period is 1 over frequency. And so if the frequency is 40, shove it in, type it in, off you go. All right, now we go back to figure 2. It says, look at figure 2. Which points on the x-axis are located at a distance a from equilibrium? What is a? In other words, the amplitude away. That would be both r and q. Better be right. Suppose that the period is t. Which of the following points on the axis are represented by the time interval t? Now, I'm going to copy this picture over so we can write on it. So we've got, let's take this idea and run with it. So when does the period happen? So let's just try these out one at a time. K and L. It started here and it ended here. Has it gone back through its cycle? No. K and M. Starts here, goes here, but is it repeating its cycle yet? It's not repeating its cycle. It won't repeat its cycle until P. Okay, so that one's no good. K and P. K, P. After P, is it going to repeat itself and be the same thing again? Yes. There you go. Now assume for the remaining parts that the x-coordinate of r is 0.2. What is the period? T-coordinate of k is 0.005. So we're going to go here. So it tells me that k is at 0.005 seconds. Now it asks, what's the period? Well, right here, from here to here, that's only a quarter of the period. So when I go K to L, there's another quarter, L to M, another quarter, M to N, there's another quarter. Well, how many of those is it? 1, 2, 3, 4. So if I do 4 times that time, that's my period. Okay. Now, how much time does it take to travel from the point of maximum displacement to the opposite point of maximum displacement? So let's just highlight that with colors. From here to here is half the period, 0.01. All right, what distance d does the object cover during one period? What distance does it travel? Well, during one period, the distance it travels is it goes from here to here. And it tells us that's 0.12 meters. And then it goes here back. Well, that travels 0.12 meters again. So the total is 0.24. What distance d does the object cover between points labeled K and N? Oh, now they're getting tricky. Okay, I'm going to make sure that number is correct. 0.12. Yep, 0.12. So let's do now, it says from K to N. So let's highlight that. K to N. So we're going to start here, and we're going to go to here. So from here to here, go 0.12. From here to here, I go 0.12. And from here to here, go 0.12. So all together, I travel 0.12, 0.12, 0.12, which is 0.36 meters. There you go. All right. Hey, that was a lot, guys. Way to stick with it. Nice job. All right. Go get them. And as always, guys, Check in with me if you have questions. I'm happy to work with you. I know this is tough doing it this way, but if you made it this far in the video, proud of you. Okay, stick with it. All right, talk to you guys soon.